I'll start right away. Space debris, what is it? Space debris defines non-functional, uncontrollable objects left behind during space missions. So anything that is out of control and serves no specific purpose or function is classified as space debris. We have various sources of debris and various sizes, which I'll go over in detail very soon. And the big problem about space debris is that the high speeds at which objects in orbit are moving can render small particles very, very dangerous to spacecraft. As a rule of thumb, an object that is larger than 1 centimeter in diameter can completely destroy any other object it hits. So when you have a satellite in orbit and it's hit by an aluminum ball of 1 centimeter in diameter, it will be completely fragmented, causing thousands of more pieces that are potentially dangerous. Space debris usually has long lifetimes in orbit because the forces that decelerate and slow the objects down so they can burn up in the atmosphere are very long. 25 years is considered acceptable, and most of the stuff stays on there for hundreds of thousands of years. And there is no effective way to actively remove those objects. So as we progress in shooting stuff into space, this problem is going to rise. These are some ground test results. You can see an aluminum ball of about 1 centimeter in diameter hitting a massive aluminum block at a speed much lower than the highest speeds in orbit, which are about 15 kilometers per second if you have a frontal collision, but usually 8 to 9 kilometers per second. This is a way of shielding a satellite. You have one very small plate of aluminum, then you put a little bit of Kevlar between those plates, and then you have the back plate. I don't know if you can see them, that the object that hit through there is splattered on the back face. So when you have your electronics on this side, then this is a very good way to shield it against small debris. But as I said, at high speeds, this won't help anymore. So I'll give you a few basics, then a few space debris sources, a few countermeasures that are possible, and some of the challenges that are interesting, especially in the field of computer science. Some basics concerning orbit parameters. This is basically all you need to know. This is the orbit of an object. This is the equatorial plane of planet Earth. And the main things you need to know are the semi-major axis and the eccentricity of the orbit, which define its shape. The semi-major axis is the radius of the larger portion, and would be this here. And the eccentricity is a value between 0 and 1 that defines the shape of the ellipse. So 0 would be a circle, and anything closer to 1 would flatten the ellipse. The other important thing is the inclination, which is this angle that defines how the orbit is tilted against the equatorial plane. The other values aren't really important here. They define how the orbit is rotated around the Earth and the position of the satellite. The other thing that's important is the perigee, which is here, and the apogee is on the opposite side. This is the point of the orbit where the object is closest to Earth, and the apogee at the opposite would be the point where it's farthest from Earth. And at the closest point, it will move fastest, and at the opposite point, it will move slowest. The most important orbit types are the low Earth orbit, which are mostly circular orbits, anything below 2,000 kilometers, which are mainly used for imaging satellites, manned spacecraft. The ISS, for example, would be a perfect example of a LEO orbit. These are the ones that are most frequently used and the ones with the highest speeds. So in terms of space debris, these are the most dangerous. The geo region holds television satellites in a way that they are fixed. When you look from the Earth, you have them orbiting at the same speed as the Earth moves, so they will always appear to be at the same position. The Molniya orbits are interesting. They've been used by former Russian satellites of that name. They have a very high eccentricity. I'm not sure if you can see it here, which caused them to go very fast. This is the ground track of a Molniya orbit, very fast around the pole, and then come up here and slow down, so that they have a lot of time over Russia to broadcast, and I think they were used for telecommunication, and then go down again. Incidentally, this is a 12-hour orbit, so on the other end, it would come over the US and stay a long time there. So I'm not sure about the Soviet satellite program, but it might have been used for spy satellites as well. This one is a typical LEO orbit, and the point you won't be able to see, somewhere about here, would be a geo orbit, just a single dot at a single spot. Then we have a thing called the Kessler syndrome, which was defined by Donald Kessler in the 70s. He predicted that explosions and catastrophic collisions, meaning those collisions that completely destroy an object and cause a lot of debris, will create large debris objects, which in turn collide with other objects and cause more debris, and form some kind of a chain reaction of debris creating more debris. And he predicted that around now this would set in, and our simulations show that it apparently did, at least in the LEO region. So if we would stop any kind of space flight, the amount of dangerous debris in LEO orbits would still increase. This means that we really have to actively remove objects from space to continue space flight in the future. What we're doing at the Institute is we're creating a model of the space debris environment. So we try to simulate every object that is out there from 1 micrometer to several meters in diameter. Our model is called the master model, which we developed for ESA. NASA has a different model called ORDEM, which has a slightly similar approach with slightly different results. And we're currently trying to work out the differences so we have a single space debris model. The idea is to get cataloged objects that are tracked by radar and telescopes. These are objects that are about 10 centimeters and above, because everything that's smaller is very difficult to see. So we create physical models of the sources that these debris are created by, and we end up with billions of objects greater than 1 micrometer. Then we go on to create a statistical model of the object flux, and we can use that to assess risks of specific satellites. So we have this master tool, which is free as in beer, which you can get from ESA or from me. I have a few copies here, and you can input a target orbit for your satellite, and the tool will generate a few graphs about how dangerous that specific orbit would be for your object. Currently in LEO orbits, with a lifetime of about 7 years, the risk of being destroyed by debris would be about 2 or 3% at the moment, but as I already said, the numbers will be rising. Okay, I'll give you an overview over the various sources of debris. These are the cataloged objects first. We have the payloads, which are the main ones, satellites, the main payload objects that serve their purpose. We have about 3,200 objects in the database, with only 800 of them functional. So 3/4 of all the satellites out there are debris. The sizes ranges around several meters. They're in all orbits, mostly in LEO and the GEO region. But for example, the Navstar satellites for GPS are somewhere in between. Then we have the rocket bodies. These are upper stages, which don't burn up in the atmosphere. You have a multi-stage rocket, and the lowest 2 or 3 stages will fall down or burn up in the atmosphere, but the topmost stage that hosts the payload will usually stay in orbit and serves as a very large target for a collision. There are 1,800 objects of those types cataloged as of May 2009, which is the basis for all the data I'm giving you. It's May 2009. Again, several meters in size and mostly LEO orbits or geotransfer orbits. Then we have the mission-related objects, which are lens caps, bowls, lost tool bags, anything that can fall off during a space flight. We have 900 of those objects in the database, 10 centimeters or above in size, and again, mostly the LEO region is affected. Then we have solid rocket motor dust or slag. If you listen to the solid rocket motor engine talk by David on the second day, you will probably have learned that they're using aluminum bits to mix into the rocket fuel for better combustion. The problem is that these aluminum bits clog up in these parts of the engine and then get spewed out the nozzle as aluminum oxide with a size of approximately, I think the largest one would be several centimeters, so about the size of a fist. These are simulated by us, so we cannot assess all of them, of course. So we simulate the solid rocket motor firings and estimate how much debris is generated by them. And we have about 180,000 objects larger than 1 centimeter in all orbits. Then we have sodium-potassium droplets. This is interesting because these were caused by a very specific type of satellite, a Russian, former Soviet satellite that used a nuclear power engine. And when one of those engines crashed over Canada, which the Canadians didn't like very much, of course, the Russians rebuilt their satellites so the core gets ejected at the end of life of the satellite and can burn up separately. But the ejection caused a few of the coolant droplets to leak, and these form little metal balls of 0.5 millimeters to 8 centimeters, so again about the size of a fist. And these are equally distributed around Earth in low orbits, which I will show you in a minute. Then we have explosion and collision fragments. So far we've counted a little more than 200 explosions and 10 collisions that have happened in the past. We simulate those events and estimate how many particles and what sizes are generated. The explosions are mainly caused by fuel remainders or battery malfunctions. So remaining fuel gets heated up in sunlight and explodes, or batteries that malfunction can explode. We have around 10 billion objects with 400,000 explosion fragments and about 100,000 collision fragments larger than 1 centimeter. So these are very, very dangerous because, of course, they all exist in very high frequented orbits. Then we have ejecta and paint flakes. These are very small particles that won't cause a catastrophic collision, but still can clog up and cause your solar arrays to fail. These are about sizes up to 3 millimeters in all orbits. We have billions of objects of that type. Paint flakes are particles from paint, of course, that loosen after some time in orbit due to surface degradation. Then we have the Westford needle clusters. This is another interesting source because in the early 60s, there were 2 experiments with copper needles that should be sent into orbit to reflect radio waves to improve radio communication. They had two experiments of that type. The first one failed completely because the needles didn't eject properly and formed clusters. So we estimate that they look something like this, so several needles stuck together and then maybe a larger boom of needles that still clung together. The second experiment was a success. It really reflected radio waves for 2 days, and then the needles started to tilt. So they were thought to stay in this position so the waves could be reflected on them, but due to perturbation forces, they tilted, and now they don't reflect any waves at all and don't serve any purpose anymore. So this is another source of debris now, but they are mostly in non-critical orbits where no other spacecraft are located. Another overview, we have the Westford needle clusters TLE background, which are the catalogued objects. Then we have the others in different size regions. We also simulate the meteoroid background, so micrometeoroids that enter the Earth's surrounding and influence. These are not technically debris, but of course they have the same effect as spacecraft, so we simulate them as well. And again, anything larger than 1 centimeter will completely destroy any object. I will now show you a simulation of all these that we developed at the Institute. I hope I can get it to work here. Takes a few seconds to load. Okay. There we have Earth. And I'll just put in all the object types. First, the satellites. And I hope you can see everything, or they move, of course. You can see the geostationary orbit, just around here. Now you can't see it anymore. This ring here would be the geostationary orbit. You can click any object and read its orbit parameters when it's cataloged, of course. If we don't have any catalog information, then of course we can't display them. So again, 3,200 objects, most of them are useless now. Then we have rocket bodies and mission-related objects, which adds another 2,500 objects. The Westford needles, which form a ring. I hope you can see it somewhere here. So this is the ring of copper needles, which should have been evenly distributed, but there seems to be an error in our model that they somehow didn't distribute evenly. What did, though, were then sodium-potassium droplets, which form this beautiful looking ring around Earth. And since the inclination doesn't change, you can see that over the poles there are no droplets. These orbits, I try to show you one. Here, for example. The objects will go around there, so they won't circle around the poles, of course, but they all form these holes together. Okay, let's see, what else do we have? Okay, let's just put in the rest. Paint flakes, slag and dust, collision fragments and explosion fragments. And it will look like this. The size, of course, is exaggerated. These dots are about 20,000 times the size of the actual objects in relation to the Earth. But you can see there's lots and lots of junk out there. We have 620,000 objects. These are representative objects, so to save computation time, objects with very similar orbits are put into one. So any of these dots can represent hundreds or thousands of objects. But of course, if I would enter the ejector, this would add another 4 million representative objects, and then I guess the GPU of this computer would fail. Okay, this of course goes for Earth space. Hackerspace currently looks like this, by the way. Okay, so we have the objects, and you can see that we really have to reduce space debris to ensure safe spaceflight for the future. Possible options are, of course, wait for natural causes, which takes a long time. You can count on the atmospheric drag, of course, which decelerates objects, or the solar pressure, which can decelerate objects too. But as I said, 25 years of time are considered acceptable and small. So other measures have to be taken. And then you have passive measures, like preventing debris from occurring, and you have active removal missions. So any kind of spacecraft that will fly into orbit, take down an object or multiple objects, and then remove itself. For passive prevention, the United Nations Committee on the Peaceful Use of Outer Space has released a few guidelines that are hopefully being followed by everyone, because of course this is a global concern for any country that wants to do space flight. We have, of course, the prevention of mission-related object release. So don't just eject your lens cap or your bolts into space, but fix them somehow so they cannot fly away. Failure-proof design to prevent any object from accidentally exploding by good design. Active satellites can, of course, take evasive action if there is danger of debris occurring. Then there are passivation measures, which is basically discharge batteries and release fuel remainder so the objects cannot explode. No intentional breakups, which means no anti-satellite tests and no space weapons, very important, because, well, these cause a lot of debris. The last anti-satellite test has increased the debris in LEO orbit regions by 30%. So one of these tests will really drive the progress forward. Then we have controlled re-entry. In LEO orbits, you can just decelerate an object with the remaining fuel so it burns up in the atmosphere, which is usually done for spy satellites, which you don't want anyone to find on Earth. And for geo regions, you use graveyard orbits. You just use the remaining fuel to accelerate the spacecraft and put it into an orbit several hundred kilometers higher or lower into a region that is not used by active satellites. So they can collide and they can create debris, but it won't harm any region that is important for spaceflight. Of course, this is just a temporary measure and should not be used for always. Now, the problems of active removal, a lot of questions are open, and there's no active removal mission that has been conducted successfully yet. So we really, really need a great idea there. But there are several main problems. For example, who pays for a debris removal mission? No one is willing to invest several $100 million for such a mission without benefit, and there are no legal obligations for anyone. So we have to develop legal guidelines, laws to determine who would have to pay for such a mission, because otherwise people simply won't do that. We have to determine which objects should be removed. This is possible. We have used the master software to determine which objects are most likely to cause debris and generated a kind of priority list to determine which objects should be removed first. Another problem, how to get larger, heavy objects into space efficiently. There was an idea, for example, to use solar sails to decelerate objects, but there is no way to get a large enough solar sail into space without breaking it. You have to have a very sophisticated unfolding mechanism. And of course, you have to prevent the sail from breaking, which would cause even more debris. So no one has successfully presented an idea here. Of course, there are orbital physics where some of the ideas simply seem to forget that you just cannot do anything in space, like fly directly towards an object, get it down, and fly somewhere else. You have, of course, use orbital physics or have ludicrous amounts of energy, which is not possible at the moment. Then some people have suggested using a spacecraft that just flies behind debris objects, Pac-Man style, and gobbles up the objects. The problem is that, especially in the endangered regions, most of the large debris comes from the side. So this is impossible unless you have a space debris-proof spacecraft, so any kind of material that is strong enough to survive such collisions, which is currently not possible. And essentially, of course, how prevent an anti-space debris spacecraft from becoming space debris itself. So you have to really be able to move it really quickly and bring it down so it doesn't end up as debris itself. So to sum up, we require ideas that don't need ludicrous amounts of energy, sci-fi technology. There's no tractor beam, no mega-maid, that require no unobtainium, and the laws of physics we are bound to. So I give you a possibility of an idea that's being followed at the moment, to have a reusable satellite and use a robotic arm, some kind of net that can capture an object, or a space tether, which is basically a large rope that you attach to a satellite and then roll out the rope, which will cause the active satellite to increase in height and the junk object to decrease, so you can grab it somehow with a tether and lower it down into the atmosphere where it will burn up. There have been successful tests with this, but so far, no debris removal mission. And our priority list shows that most of the objects on the priority list are of the same type. So the same type of rocket body, the same type of large satellite. So you can design such a spacecraft to attach to a specific kind of object. And of course, for the future, you can design rocket bodies with a certain mechanism that space tethers or nets can hook onto. Okay, for computer science, this is interesting because mainly we have a huge numbers of objects. I was talking billions of objects that have to be calculated on. We have complex algorithms, especially when it comes for things like atmospheric drag. And for our program, we basically take one point in time, which we simulate, and then go from there and propagate all the objects. So we predict where they will be 2 years later. And this means that we have to do those calculations on every of these billions of objects, which of course requires large amounts of computation power. And of course, my colleagues will hate me for this, but engineers seem to like Fortran because it's always been there and it's easy to learn. But if you want to do some more sophisticated stuff like databases, graphical user interfaces, networks and stuff, then with Fortran, you're basically stuck. A possible solution that we're going into is GPU computing. The simulation I've shown you, for example, can handle those 600,000 objects very easily. A CPU would slow down to unacceptable frame rates at about, let's say, 20,000 objects. So that's a real speed up we get here. In this simulation, the object propagation is done on the GPU via vertex shader. So every object is basically one vertex, and its position is determined by the shader on the GPU. So this shows a very huge speed up, which we can use in the same way for our computational models and our debris source models. We've had first tests with CUDA and OpenCL, which are basically libraries that allow general purpose computing on graphical CPUs and graphical processors, and we can achieve the same speed ups than we achieved on the animation. But the problem we're currently facing is that accuracy comes at a high performance cost. Shaders are not optimized for the kind of accurate calculations that we need. CUDA and OpenCL are a bit better there, but double precision floating point, for example, comes at half the speed of single precision floating point. In a good case, on a special Tesla GPU, specially built for GPU computing, on a usual consumer level graphics card, double precision would be 1/12 of the speed of single precision. Okay, in conclusion, we have billions of space debris objects that are potentially dangerous. I think about several 100,000 of objects larger than 1 centimeter that can really wreak havoc on existing satellites and other objects. This large number versus only 800 functional satellites that are in orbit at the same time. So the amount of debris is massive, and the large objects have to be removed so the amount of debris will not increase and make spaceflight impossible in the future. And I give you a brief overview. I'll show you the simulation again about how high-performance computing can be used to calculate these models. This works, of course, because all these objects are independent from each other and can be calculated in parallel on the GPU, at least until it comes to things like collisions. Then we would need different models, but we're working on that. The Master 2009 model is free as in beer, as I told you. I've got 25 DVDs here, so if you want to grab a copy, you can come up front and get one, and if there are no more left, you can email me and we will send you a copy free of charge. You won't even have to pay shipping or something. We'll just send you a DVD if you leave us our shipping address. And I'll show you the program really quick. Hope I have it here. Okay, so this is the graphical user interface of Master 2009, which is basically laid over the master tool, which is a command line tool, so you can use it in scripts and stuff. Give you a target orbit scenario, for example, where you enter your target orbit. For example, you start your satellite at May 1st, 2009, and end the lifetime 1 year later with a semi-major axis of 7,000 kilometers. So that's a typical low Earth orbit, nearly circular. Then you can select various sources of debris that you wish to account for. When there are collision or explosion events, we release new clouds of debris that you can copy into the program and then activate here. So whenever there's a collision in space, you will have the latest data. Then you can define surfaces. The simplest one would just be a sphere, so a spherical satellite representing your object, or you can be precise and enter all the surfaces that your satellite has. And then select which kind of plots you would like to see. And then just execute master, and I hope it works now. Take some time. So basically now it's running the command line tool on the input it generated and uses nuplot to create beautiful prints of what's coming and show them on the graphical user interface. Okay, it's finished. Somehow move this away. Not sure how. I think it don't work Ubuntu yet. Okay, here are the plots. A little small on the screen, unfortunately. The y-axis is always the object flux. So object impacts per square meter of satellite area per year. And you can plot over various attributes like the mass of the impacting object. So you can see that most of the objects, nearly all of the objects that impact are less than 1 kilogram in weight. The diameter of the objects that will hit you, so for this orbit, these are very, very small objects mostly, and the centimeter objects, which would be around here, are of course the least, but also the most dangerous. I will show you another animation, which I forgot to do. Okay, this is one explosion that occurred in space. Very hard to see. This is the spot where it happened. And this is the amount of debris that we simulated from this explosion. And when you start the animation, you will see how the cloud will distribute over time and form a neat ring like this. The interesting thing is that every object will go through the point of origin. So when you have a satellite that, for example, has an orbit going around here, through that point, then you have a problem. And if we left it running now, you would see that this cloud would evenly distribute around the Earth, just like the sodium-potassium droplets that I showed you earlier. Okay, that's all I have. As I said, master DVDs are available here if you're interested. There's a lot of documentation on the DVDs, on all of the models in very large detail, so you can have a look there or email me for any questions. Thank you.
Okay. We have about 15 minutes for questions. If people would like to come in and speak at the main microphone, that would be wonderful. We also have questions coming in from online. That's okay. So it's about 15 minutes, and then I'm going to give you some announcements at the end, and that's about it.
Hey, you talked about doing the calculations and maybe going to a GPU solution.
Yes.
And I wasn't sure, but it came across to me that you're doing everything on one computer. Is that correctly?
I'm sorry, I didn't get
That you're doing the whole calculations on one server on one, or a bunch of CPUs in one computer, or are you using multiple computers next to each other to do the?
That's the plan for the future. As of now, I
Could
don't
you-
have access
Can you just
to
repeat
a
the question?
GPU cluster. We have one at university, which I'm trying to get access to. But currently, I have one Tesla GPU, which is a special GPU computing card, and a consumer-level graphics card, and I use those to simulate the objects.
Sorry.
So when you look at night sky, it's quite usual to see, I think it's called the shooting star in English, so meteorites.
Mm-hmm.
The explanation given in schools, for instance, usually says that these are natural, like grains of sand that enter the atmosphere. So I wonder how much of that today is actually artificial artificial objects like space debris, and how much of that is natural background of meteorites.
Okay, so how much meteoroids and how much space debris or anything? I
Is
don't.
it dominated by artificial? At this point in time, is this dominated by artificial objects or not? Or
That's an interesting question. I don't have any numbers on this, but you can usually determine when it's an artificial object that it usually breaks up, so you have a cloud of objects. Of course, that can be a breaking up meteoroid, but usually that's some kind of debris that's breaking up and burning up in the atmosphere. So when you have a really large cluster of objects, then this is space debris in most kinds. Or a spy satellite that someone doesn't want anyone to find.
Hi, you mentioned Dome was willing to pay for the cleanup. Presumably the satellite insurance industry, they would reduce their costs by reducing the chance of one of the satellites they're insuring being destroyed. Is there any sort of movement from them to say, we'll put a bounty of a couple of $100,000 or $500,000 per one of these large rocket stages that gets removed, or has there been anything like that?
So some kind of space debris insurance, a company that will insure space debris impact.
Well, there's an existing insurance industry for satellites. So if you're launching a satellite, that company, those insurance companies, I assume, will, if your satellite is destroyed by debris, will pay out compensation depending on what kind of insurance deal you have with them. I should imagine that the insurance industry doesn't want to pay out. So if they can reduce the debris risk, they increase their profits. So at that point, it makes economic sense for them to pay bounties to have the debris reduced. Has there been any sort of do you know of any communication with the insurance industry to ask, are you willing to pay out? Have they done the sort of actuarial calculations as to what's a good price to set as a sort of market for reducing debris?
Okay, as far as I know, there's no such thing yet, but I'm not a legal expert. I'm a computer scientist, so I have really no idea about that. But that's a really good question and maybe a very good idea, so I'll have a look into that and
Thank you.
maybe. Thank you for the question.
Do we have any more questions? We have a good 10 minutes left. If people.
I have one question.
Sorry?
How exactly do you simulate the collision cascade, the production of debris?
We don't have a model to simulate a cascade, but we have models to simulate certain events. So what we do is we simulate one event, then look where all the particles go, and then assess, try to calculate the possibility of one of these objects causing another collision, and we put that into the model. So if there's a collision and you simulate another year, for example, then the probability with which one of these generated objects will cause another collision will be accounted for.
Come on, there must be something else. Have we not got anything coming in for online? Come on. We've got a whole 10 minutes with him. Must be something.
I guess we're all tired.
The list you calculated of the priority list of targets, is that online somewhere?
No, that's currently not available. We did that for a third-party institution who might make it available in the future. So if there's anything, it will probably come out on our institute's website.
Is it sort of a fairly obvious list? I mean, if you just looked for large rocket bodies in crowded orbits, would it be fairly easy, or is it actually, are there any surprises in there?
There are some surprises, and most of this list is comprised of old rocket bodies, which is not surprising at all because satellites can usually be removed by other means, for example, controlled re-entry. So the rocket bodies are what's staying up there, and those are the ones that cause most collisions and explode most. So these are the most dangerous objects, so it does make sense. There were some objects that we don't have data for, mainly US spy satellites. Of course, we get the object data from the US military, but they don't put in their own spy satellites. So we don't know if there's any, but if there's an endangered spy satellite, then the operator will surely know and wouldn't want anyone to remove that object for him, of course.
Actually, I've got one question.
Okay.
Have you thought about using the technology used by visual effects companies? Visual effects companies are meeting exactly the same sort of issues in terms of simulations of objects, having to parallelize object environments, very, very similar issues about whether they run on a CPU versus GPU. Have you actually talked to any of them? Because a lot of them use open source products and are part of open source projects. And I think also they're kind of interested in anybody who knows computational skills and the underlying math skills, because they say they're finding those people are rarer than hen's teeth. So you might well actually find people who are desperate to work with you.
We're currently the only ones who do this on space debris, but in essence, it's all numerical calculus. So there are lots of other scientists that go into this field, for example, in pharmacy, in physics, and of course in the video game industry too. So I mainly get papers from everywhere and try to adapt what they are doing to our courses.
It's okay. I've just been listening to stuff from SIGGRAPH about these sort of issues, and it seemed remarkably similar to what people are worrying about at SIGGRAPH right now.
Okay, I haven't followed the latest SIGGRAPH, but thanks for the tip. I will surely look into that.
Do we have anyone else or anything else coming up?
Do you have any simulations what will happen if the launches go on as is, without any reductions or capturing of debris and deorbiting it? So when will this Kessler syndrome be really problematic?
I don't have any charts here right now, I'm sorry. But there seems to be some kind of break-even point in about maybe 60 years. I'm not sure if I remember the numbers correctly, I'm sorry. But there will be a point where taking measures to prevent space debris that may be very expensive will cancel out the cost that will be caused by satellites rendered unoperational by space debris. So in about, I think it was something like 60 years, the cost will be cancelled out. So you invest something now to decrease the cost in about 60 years. Thank you.
Okay, looks like we're coming to an end. So, can I thank Merrick for an incredibly interesting and frankly